Hello, and welcome to our second broadcast of Energistics Transfer Protocol Paves the Way for Remote Drilling Support Improvements at Statoil. Welcome, my name is Janice Shea, and I will be your moderator for this session. Just to help us get started, little housekeeping. As you can see, you have an audio panel, and this will allow you to ask questions. And you can do that throughout the broadcast. To help ensure a pleasant listening experience for all, microphones have been muted for all attendees. And we do have a lot of ground to cover, so we'll take questions at the end of the presentation. But you can type your questions in as you think of them along the way. And just to let you know, we have disabled hand raising, and the reason for that is because we want to make sure that we capture all the questions. And if we don't get to some during the webinar, we'll do our best to answer them via follow-up email. So just to get us started, we just have a brief poll question. And in this case, we'd like to know if your company uses Energistics standards today. And you can go ahead and vote really quickly. We'll give it a couple moments for that. Okay. Alrighty. We have 83% who are using Witsmell today, and 8% using Energistics Transfer Protocol. So hopefully we can increase those numbers. All right. So I'd like to start by introducing our presenters today. Thomas Holland is Operational Manager for Statoil's Real-Time Drilling Center. He has worked with real-time data solutions in Statoil since 2002, and when not working or spending time with his family, he is a dedicated follower of the Norwegian soccer team SK Brann, which according to Thomas is widely renowned as one of the best soccer teams in Europe. So I'll leave it to you to agree or dispute that. And we also have with us Jay Hollingsworth. He is Energistics Chief Technology Officer. Jay is responsible for the technical adequacy of the standards stewarded by Energistics, including Witsmell, Protomel, and RescueMel, among others. Under Jay's leadership, Energistics has realized the goal of an integrated family of standards based on a common technical architecture. In addition to providing technical oversight, Jay is the main trainer for Energistics and represents Energistics on various technical committees of other associations and standards bodies. Welcome, Thomas and Jay. So today we're going to just very briefly touch on who Energistics is for anyone attending who's not familiar with us. And then we'll spend the majority of our time talking to you about ETP and then even more importantly, how it's being used today by Statoil. And then we'll save time at the end for question and answer. So just quickly, Energistics is a global nonprofit membership consortium. We've been in existence for 27 years now. Originally, we were called POSC. And I think the key takeaway here is that we're member-funded and member-resourced standards organization. But it's important to note that Energistics is not a vendor in the traditional sense of the word. What we do is bring companies together to come up with solutions for the industry to help facilitate what you do. And with that in mind, the standards we steward have been developed by and for the industry. So I think sometimes people think that this is an academic exercise, and I just want to make sure that people understand that it's absolutely not. The development that's done has been based on real-world problems that companies are trying to address every day. And we are working together to come up with solutions that meet those requirements and address those real-world business challenges. So just to give you an idea, this isn't necessarily everybody, all the companies that are involved with Energistics, but this is a good cross-section of the companies, oil companies, service companies, technology, other standards organizations, academic and universities as well, who work with us on a daily basis. And then just a kind of a bird's eye view of the Energistics family of standards. At one point, each of these standards grew up in and of itself, kind of in a siloed environment, starting with the drilling standard, WITSML, then PRODML, or for production, and our most recent of the ML standards is RescueML, of the domain standards is RescueML, which addresses reservoir and earth modeling. The key part here, though, is that these standards, while they grew up in a siloed manner, we now are able to use all of them together to address cross-operational workflows. And we're able to do that because they're based on a common technical foundation, what we call our common technical architecture. So all those common elements like unit of measure and properties and overall architecture, all of those things work together so that you can use any of the data objects across all of the standards to address a particular workflow that you may have. And a key part of that common technical architecture is what we're here today to discuss, which is the Energistics Transfer Protocol, arguably our newest specification, but already receiving a lot of interest and note across the industry and even, I think, outside of the industry. So Jay may touch on that a little bit. So with that in mind, I'm going to turn you over to our Chief Technology Officer, Jay Hollingsworth, to talk to you about ETP.
Morning or good afternoon or good evening, everyone. Oh, thank you. I do there. Yeah. So we're here to talk about the Energistics Transfer Protocol. In summary, and we're going to go into this in a little bit more detail, obviously, ETP is, we call it ETP, and it's a data exchange specification. It enables real-time data transfer between any two running applications. It's not specific to any particular kind of data, WITSML or PRODML or whatever. It's the exchange specification that's used to move anything between applications. ETP is delivered both as a specification document, and we have a lot of sample code that's been contributed by various members. Then I'll explain in a little while how one might go about getting that. And it works from a computer science perspective just by sending messages. So we send little bitty messages from a producer, a consumer of data to a producer of data, and then the producer sends a message back to the consumer. We don't use the words client and server typically. We use these words producer and consumer, or a sender and a receiver, because client and server has a particular meaning in computer science. But anyway, we send these messages back and forth, and the messages are grouped together into what we call protocols. And really describing the little messages and how they're grouped together into these protocols is what makes up the standard of the Energistics Transfer Protocol, ETP. Like I said before, you don't have to have a server. It's just a sender of data and a receiver of data. And we'll talk about all of that stuff in a little bit more detail. So, in the world of real-time data monitoring, which is what WITSML's use of ETP, part of what WITSML's use of ETP will be. This is the way real-time monitoring looked up until about the year 2001. This is a picture of the Amoco Critical Well Facility, and you can see, in fact, that it was focused on a video connection from the well site to, or the rig site, into a central office. And you can see somebody's picture actually on that television screen. But if you look at the screens to the right, you can see they actually moved data in real time along with this. So the Amoco Critical Well Facility in Tulsa was the first attempt to move real-time data from a drilling operation. And the first real-time drilling data center was in the Superior Oil Company in Lafayette, Louisiana in 1981. And that data center was actually moved to Dallas and then was moved to Houston and still exists as part of ExxonMobil. So real-time monitoring has been happening for quite a while. There was an earlier standard that attempted to enable this called WITS, which was the Well Site Information Transfer Standard. We still find it in use sometimes, especially among equipment on a drilling rig. And what you'll see is something called WITS level 0. It's a really simple ASCII format, and it doesn't do the same things that the industry needed to be able to do, starting sometime around the late 1990s. So Statoil and BP got together and created a project they called the Drilling Automation Real-Time, which was intended to help replace the proprietary systems that were in use up until that point. And then they brought, Statoil and BP brought Schlumberger, Halliburton, and Baker into that group, and that was the beginning of WITS-ML. So WITS-ML has been the dominant real-time monitoring standard up until the present day, basically. The data that's moved via WITS-ML is not truly streaming. It's what we think of as near real-time. The data is transferred using XML, so from an IT perspective, it's pretty simple. The data, at least, is pretty simple. And the way that it works is a client application constantly asks the server if it has any new data. So, but the way it's architected in reality in the field is that an operator typically will connect to a service company's site, Schlumberger, Halliburton, Baker, Weatherford, Paves, Kongsberg, Petrolink. There's a lot of companies that offer this kind of service. And then the service company then connects to a server which is at the rig site. And then the rig site WITS-ML computer server then communicates to the servers of the various contractors on the rig. So the mud logger and the directional driller and so forth may have their own computers. But what this means is that there are several hops. So as a user, your computer is asking a service company server if it has any new data, and then from time to time it asks the rig site if it has any new data, and from time to time that server asks the service companies on the drilling operation if it has any new data. So this fills up the bandwidth with a lot of requests for data, plus the data is kind of old by the time you get it. It could be 30 seconds, a minute. Thomas will talk about that a little bit when he talks about the Statoil use case. So the community felt that it was time for a technology refresh in the way WITS-ML works. The WITS-ML XML objects were kind of okay, but the underlying way that the data travels from a sensor on a rig through to either a visualization environment like you see in this real-time operations center or into a technical computing user's application, that underlying stuff needed to be refreshed. So a project was begun called ETP. The project, as I've already described, was to have much higher frequency data and low latency. Low latency means how old the data is. So we don't want to have to wait a minute or 3 minutes or 10 minutes to get a piece of data from the field. We want it to come now, and we want to be able to push a lot more data over the telecommunications channel. This method of transmission needs to be friendly to firewalls so that it's easier for an operator to deploy the solution. If it requires your IT people to do a lot of special networking and open ports and drill tunnels through firewalls, it's just that much harder to get it into your own company. And so one of the requirements for this project was to use as much internet technology as possible so we could piggyback on the already open connections that you have to get to your internet from your work. And we wanted it obviously to be built on as many broadly accepted technologies and standards as we possibly could and not have a lot of licensing. And the business basically said they wanted this kind of thing now. So you can see some of the use cases that were originally intended to be supported, but the truth is that the standard as it exists now supports a lot of different diverse use cases. And kind of what was said in the beginning is basically, we don't care how you get the data. We don't care if you use a pigeon with a jetpack. What we want is our data, and we want it now, and we want it fast. And so this is the famous pigeon with a jetpack. And you can look at these use cases, the ones you can think of. We want a sensor to stream data into a data store, a sensor to stream data into an application, one data store to be able to synchronize with another one, et cetera, et cetera. So this is a list of the protocols, and I've already told you that a protocol is just a bundle of messages. And so we've taken the messages we have and we've gathered them together into these 9 what we call protocols. The ones important for this, ones important for this discussion are really protocols 0 and 1, which is about streaming real-time data. Protocols 2 through 8 are the replacement for the old server store API that WitsML had, and parenthetically it's a replacement for the API that ProtoML had as well for interacting with a server. So ETP also includes a replacement for the old SOAP APIs. But the ones we're really caring about in this conversation are the channels 0 and 1, protocol 0 and 1. Protocol 0 just creates a session. So I send a message to a sensor and say, am I allowed to talk to you? And the sensor says yes. I ask the sensor, do you support compression and encryption? And which of the WitsML objects do you support? And it sends me a message saying, yes, I support encryption. Maybe I don't support compression. And these are the WitsML objects I support. And then I ask it if I can have a session with the sensor, and it tells me yes, and gives me a name for that session. And that's all there is. It's just sending messages back and forth. On protocol 1, I then send a message to the sensor asking it what data it knows about. It sends me a message back saying, let's say it's a hook load sensor on a drilling rig, and it sends me a message back saying, I know the calculated hook load, I know the raw voltage from the sensor, I know how many days it's been since I've been calibrated, whatever the sensor might know about. Then I send a message back saying, okay, please begin streaming to me the calculated hook load. It sends me a little message back saying, okay, I'm going to send you that data as a series of floating point numbers, and the next byte on the wire is the hook load data, and I get it until I ask it to stop. So from a programmer's perspective, it's pretty simple. Just exchange these messages. It's obviously a little bit more complex than that. We have features built in there to support reconnecting to the sensor in case not if, but when the connection is broken, we need to be able to reconnect. We need to be able to optionally catch up on all the data we missed. And there's a lot of other features that are in the protocol. But at its simplest, it's just exchanging these messages back and forth. The technology that we chose to use for this, you can see a list on the screen of those technology choices. The important thing is WebSocket. So we chose to use a normal internet protocol for true streaming real-time information. And it uses the regular ports that your company already has open to allow internet traffic, which is typically called port 443. And we use JSON and a lot of the other technologies that are sort of related to the new generation of the internet, HTML5. Finally, I said I was going to mention how we're distributing it. The specification documents for ETP are freely available for download from the Energistics website, like all of our standards. Also, there are links on our website to lots of source code. So if you want to get started with ETP, there's C#.NET implementation. There's a JavaScript implementation that runs right in a web browser that some of our members find really convenient. There's also Java and C++ implementations of ETP that are available via our website. The source is there. There are assemblies already built for your developers. But the key thing is that all this code is contributed and maintained by our members, which we think is a really good thing. And we have stories, rumors that some of our members may be contributing some other languages. And as that happens, we'll announce that, and it'll appear on our website as well. And we especially want to note that there's a fully featured developers kit for ETP that was contributed by one of our members called PDS. And so again, that's on our website, and you'll find links to it, to our Bitbucket repository from our website. And with that, I think I'm going to turn it back over to Janet.
Okay, thanks, Jay. And now I'm going to turn control over to Thomas Holland.
Thank you, Jenna. For those of you who don't know me, I work in Statoil's real-time drilling data center as operational manager, and I've been working with real-time drilling data all the way since 2002. What I'm going to talk about today is how we in Statoil, together with Kongsberg and Baker Hughes, are utilizing ETP from Energistics to significantly improve our abilities to provide remote support from onshore to our drilling operations. So first I'm going to talk about the business case that we are targeting. Then I will go into details on how Statoil, Kongsberg and Baker Hughes joined forces to utilize the ETP on the existing version of WITSAML. And finally, we will elaborate on the next steps and provide recommendations for how other operators with similar business needs may take advantage of this new technology, which is now available in the market. Statoil have at any moment many active rigs, and a huge number of service companies are at all times involved in performing services at rig site. The actual MWD, LWD and mudlogging services are normally performed by one of the major service companies like Baker Hughes, Schlumberger or Halliburton. These companies typically have personnel at rig site, and they have extended their network from the rig to their onshore support center. So for these service companies, it is relatively easy to get access to real-time drilling data. But we also have a huge number of other companies, here exemplified by Archer Oil Tools, who have to fly out personnel to rig site in order to perform their contracted work. For any operation, there is a long list of different companies involved performing services like completion, cementing jobs, wireline, DMI plugs on pipe operation, casing running, fluid services, etc. And with a traditional work process, many of these companies have limited amount of real-time drilling data available in their onshore support center. And they need to fly out their experts to the rig site in order to perform the contracted work. And this is very expensive. They need to wait for available bed space, book helicopter flight, wait for the operation to be ready, perform the work, occupy bed space again, waiting for the helicopter to fly them back. And with a more modern work process, we reduce the number of people needed at rig site in order to perform all these jobs. And this can be performed by having access to low latency real-time data from the operation in the various contractors' operation centers onshore, combined with cross-trained resources at rig site. This is an example from a Statoil field. This is a DMI plugs on pipe operation where Archer Oil Tools are performing the work. The rig site operation is supported by the onshore Archer operation centers who are in direct contact with cross-trained resources at rig site from Kosa Deutag. In order to optimize the onshore support and hence minimize the resources needed at rig site, there is identified a need for UHF, CCTV, and lower latency drilling data available in Archer Oil Tools Operation Center onshore. The business case, as outlined in green, for improving this work process is huge. By modernizing, a potential for reducing the personnel on board by 2 to 3 persons per job was identified. And only for DMI operations, this can save several thousand offshore days for Statoil compared to the old traditional work process. There are many things which need to be in place in order for remote operations to reach its full potential. First, you always have the HSE aspect, which always needs to come first. Then you need to revise the contracts between operator and contractors. You need to inspect the capabilities of the companies, their operation centers, their maturity with regards to remote support. You need to look into network, connectivity, hardware, and last but not least, access to real-time data available onshore with very high quality and very low latency. And the last point here is very important and also very challenging, since the efficiency and quality of the remote support is directly linked to the availability, quality, and low latency on the real-time data available onshore. Not only do they need the full dataset available, but many of these support centers need very low latency to maximize the remote operational support. Some of them have identified a maximum of 1 to 2 second total latency, and this includes the network latency. This need is made even more challenging since we experience that the number of channels needed onshore are growing and the sample rate for each channel is increasing. With the available technology in the market today, providing high frequent low latency dataset in a standardized manner have proven challenging and often impossible to achieve, since the current available protocols typically use what we call a query response mechanism. Every target data store continuously asks for new information, receives a response, then asks for more information, receives a new response, and so on. This is not efficient and introduces latency. And this latency is then further multiplied, since there may be many hops and intermediate stores involved before the data are stored in the data store used by the remote support team. It is not uncommon that we see total latency up to over 30 seconds, and this creates a remote support challenge, thus increasing the need for personnel on board, which again drives up cost. This is where WITSAML with the new ETP protocol from Energistics comes into play. This protocol establishes a connection all the way from the source server through multiple hops to the target data store. And once the connection is established, data is continuously pushed from source to target. When the ETP protocol was created, the design criteria for the protocol was to support high-frequency data transfers with low latency. It seemed a perfect match for the business problem we were trying to solve. Given our high-value business case, Statoil wanted to leverage the power of ETP as soon as possible. Initially, we were under the impression that we needed to wait for a new version of WITSAML, WITSAML 2.0, to be adopted by the industry before we could leverage ETP. But talking to our technology partners in Kongsberg and Baker Hughes, we discovered that the protocol could be implemented on the existing industry-adopted version of WITSAML, which is version 1411. And this was later also confirmed by Energistics. So Statoil, Baker Hughes, and Kongsberg Digital started to upgrade the technology components needed in 2016. Baker Hughes upgraded their acquisition system at rig site to support sending of real-time drilling data from the rig site with ETP. Kongsberg upgraded their Sitecom software so that they would be able to both receive and send data using ETP over WITSAML 1411. And Statoil provided live test data from our operations so that we could continuously test and verify the implementations. The first version of the ETP implementation was completed in 2016, and we tested the capabilities streaming data live from a drilling operation in the Troll field in the North Sea. For the initial data transfer, the following surface mnemonics were chosen, as these mnemonics have a high update rate during drilling operations. These mnemonics were pulled directly from the acquisition system's real-time memory, formatted into binary ETP channel data objects, and sent to the target Sitecom with XML server in under 10 milliseconds. This meant that the data was made available to the consumer almost immediately after it was available in the acquisition system. And the result lived up to our expectations. And in this video, you will see that there's hardly any latency transferring data from Baker Hughes rig site acquisition system to the Sitecom onshore with XML server. The actual latency was close to the network latency, and the network latency is very low for the Troll field, where we have fiber optics connectivity to onshore. Based on this promising pilot, Statoil, Kongsberg and Baker Hughes immediately initiated activities for making this technology ready for full production, with the goal of deploying it for all Statoil drilling operations where Baker Hughes are providing drilling services. We are also now running a series of tests verifying that the technology is future-proof by streaming a large number of channels, and we are also streaming channels containing higher frequency data. The preliminary results from this testing indicate that the ETP protocol seems very scalable, both with regards to extending the number of channels transferred and to increase the sample rate without a significant negative effect on the latency. We hope to be able to release some more detailed numbers on these results in an upcoming SPE paper. We have also demonstrated that the ETP protocol turned out to be relatively firewall friendly, which has earlier been a showstopper for other similar streaming protocols. We did encounter some challenges in this area, but they turned out to be relatively easy to solve. Another small issue which required handling was network dropouts, since ETP uses an open connection. If the network drops out, the connection has to be re-established. But this was easily overcome using a retry mechanism. The current plan is to have ETP fully deployed for Statoil drilling operations where Baker Hughes are providing drilling services later this year. This technology can help optimize remote operational support for many different work processes and services. Here is an example from a Statoil rig, and as you can see from the extensive set of work processes where low latency real-time drilling data onshore is needed, this shows that at least for us, there's a very high business value in implementing a robust low latency data transfer from rig site to internal and external operation centers. Our work so far indicates that the version of XML adopted by the industry today, combined with ETP, seems to solve the problems we have today with too high latency, streaming data to all the involved onshore operation centers, both inside and outside our company. In Statoil, the combination of XML and ETP is recognized as one of the key enablers for providing more efficient remote support to our operations, and thus reduce costs and reduce the number of personnel needed at rig site to perform the various operations. Implementing the standard in Kongsberg and Baker Hughes technology has been less challenging than expected, and the upgraded technology components are now commercially available for other operators. From Statoil's perspective, we would like to thank Baker Hughes and Kongsberg for joining us in performing this important technology upgrade. Ted Abrahamson from Kongsberg, Pete Morrison and Peter Geddes from Baker Hughes, and Kjell Inge Meisal from Statoil are all good contact persons if you want to know more about the technical aspects of this technology adoption. We also hope to be able to provide more details in an upcoming SPE paper. And there is also an Energistics case study, which we hope to release shortly with more details, so stay tuned. That's it for me, and back to you, Jenna.
Okay. Thank you very much, Thomas. I really appreciate everything that you shared with us today, and I'm sure our listeners do as well. Before we turn over the webinar to our listeners for Q&A, just have a quick poll question for you. And that is, based on what you've learned so far today, would you be interested in using ETP in your company? Very interested to get your feedback on that, and certainly there will be more webinars coming up in the future that get into more technical detail about how you'd actually implement ETP. So I think we're going to start working on that pretty quickly. And then we hope at the end of the year to have a webinar about ETP and RescueML. So stay tuned for that. All righty. So go ahead and close and share the results. And so 93% are interested in using ETP, and the other 7 are undecided. So that's good. No no's. Well done, Jay and Thomas. So let's see if we have some questions. Oh. So by all means, do enter your questions in if you have some. All righty. All right, so I'm not seeing questions from our listeners today. Just looking to see if, oh, okay. So yes, the presentations are going to be available. We are recording this today, and we'll be posting it in the next day or so. And let's see. Also, we have a broadcast, the last broadcast that we did on May 24th, also has been posted, and there were quite a few questions there that were asked at the time. So one of the questions, oh, and before I forget, the handout of this presentation that you've seen today is available for download right from your control panel here. So if you haven't already downloaded it and you're interested, go ahead and do that. One question that's come in is, how secure are the transfers? So I should note that joining us also, in addition to Jay and Thomas, we also have with us today Ted Abramson and Trond Våge from Kongsberg, and Pete Morrison and Peter Geddes from Baker Hughes. And we also have in the room with us here Robert Shavey, who is one of the architects of ETP as well. So as far as the security of the transfers, I'm going to turn that over to Jay, and you can talk about that.
Yeah, I mean, so the security is handled by typically by the underlying layers of the WebSocket transport protocol, but ETP does include an authentication mechanism which is based on JSON web tokens. So the whole system is designed to be secure from those two perspectives. So you have authentication at the time you open a connection, and then whatever encryption or other methods you may choose to use along the way if you're concerned about a man-in-the-middle attack. That's handled by the underlying WebSocket protocols.
Okay. Another question is, was the schema completely changed from WITSML 141 to ETP?
So those are two different things. Remember, ETP is just a description of how you interact between two computers. ETP could be used to move MP3 files or photographs. It's just a transport protocol. But if the question really is, was WITSML 2 completely changed from WITSML 1.4, the answer is some things were changed, and some things are pretty much exactly the same. So the well and the well bore and the trajectory and you know, a lot of those things are pretty much the same, but some of the objects the WITSML community felt needed to be upgraded. So the cement job was rewritten largely by Robert, who's here in the room, led by Halliburton. The stimulation job object was largely rewritten, led by Schlumberger. The mud log object was completely rewritten, led by Edward, I guess, more or less, from Geologics. And so the one that's changed the most is the log object, because instead of sending the real-time data via XML, like you did in WITSML 1.4, now you stream it via ETP. So the log object is completely different because it's largely replaced by ETP. So the question really is there a difference between WITSML 2 and WITSML 1.4.1? If the question was more, is the API from WITSML 1.4.1 replaced, it's completely deprecated and is totally replaced by ETP.
Or 2.0.
For WITSML 2.0, that's true.
Thomas?
This is Thomas from Statoil again. Can I add a little bit of information onto that? What was really good for us here was that we could actually implement ETP directly on the WITSML 1.4.1.1 without having to do any changes to the logical data model. So we could use the well bore, the log object, the trajectory, everything the way we always have done it. And this made the transition a lot easier because we didn't have to both change the logical data model and the transport protocol at the same time. So we could actually use ETP on our current WITSML 1.4.1.1 data stores, WITSML data stores, which was one of the reasons why we were able to do this fairly quickly.
Okay, thanks, Thomas. All right, so another question we have is, what sort of maximum data rates have been achieved?
Yeah, I think I'll have to ask either Kongsberg or Baker Hughes to help me answer that.
Okay, from the...
Go ahead, Dick.
From the Baker Hughes side, we're currently streaming the data at 1 second data rate at the moment. From a test perspective, we can obviously go a lot higher, but we are limited from our acquisition system on what data rate we can update that data at. So the actual streaming we're doing at 1 second.
Yeah, Ted here from Kongsberg. In the actual test, I think the mnemonic set was quite low. I think it showed Thomas 11 different mnemonics, and it was like in data. So obviously it was not a big stream of data. In Kongsberg, we have an internal test lab where we have an enterprise system set up, and there we have had 10,000 data points into one server, distributed to 7 other servers, and that's been working fine with a 1 second data rate. I think the CPU load on receiving that load is below 5%. The CPU load when also sharing to the 7 others is below 15%. So from our perspective, the capacity of ETP is more than sufficient to give an enterprise scale server system for WITSML.
Okay, thanks guys. Question for Jay or maybe Robert is, can you briefly say why using ETP like MQTT, AMQP?
Well, the group that developed ETP obviously looked at AMQP, MQTT, NiFi, DDS from the object management group. There's quite a few protocols. There are RESTful protocols like Ajax and Comet. You know, there are lots of other protocols out there. The two key requirements that drove us to not use those are, one, that it has to be two-way. Because remember, we don't have a server and a client. We have a producer and a consumer of data, and they send messages back and forth to each other. Most of the other traditional Internet of Things protocols, it's a one-way trip only from the sensor or the server to a client application. And we had to have something that communications could go in both directions simultaneously, full duplex communication. And WebSocket supports that. The other thing that the other protocols can't do is dynamically decide which of the channels you're going to send. With the other protocols, it's declared sort of at the time you compile your code that if I connect to a hook load sensor, it has 97 channels and this is their names and this is the structure it's going to send. Whereas with ETP, I can dynamically ask that sensor what data it knows about and then ask it to send me only 3 of those channels. So I'm not filling up my telecom link with a bunch of data that I don't care about. Some of the newer ones, as I mentioned, like DDS and NiFi, have some features that let you sort of discover the existence of those services, but they don't have the ability to ask that service to dynamically shrink the amount of data it puts on the wire. A modern offshore platform may have tens of thousands of channels available on it. And in a drilling operation, you know, what Thomas is talking about, a drilling rig from a fixed platform like Troll A, you know, there may be 10,000 channels on that rig, but on a floating drilling operation, you also are going to want to know things that are related to the ship itself and what's the weather and the response of the ship to the weather and what's the current state of consumables available. And there's lots of other data that you're going to want to put on that same communication channel. So being able to limit it to the data that you need to ensure safe operations is important. So full duplex communications and the ability to dynamically configure which channels are sent are the 2 reasons to not use AMQP and MQTT.
Okay, thanks. So another question is, does Statoil plan to use ETP to support even WITSML data transfers with the use of the ETP standard for transfers from rig to town purposes only as a hybrid solution while we await others to upgrade their rig site system?
Our plan is, we are currently using WITSML 1411 for real-time drilling data streaming from both rig site servers and other WITSML servers. And our plan is for real-time drilling data to upgrade to using WITSML with ETP for all real-time drilling data usage onshore.
But presumably, though, I think that when WITSML 2 is widely adopted commercially, then you'll consider upgrading to that as well.
Yes, that's correct. We see we harvested the potential of ETP now because we noticed that it was possible to adopt that. And the next step, Jay, is to, along with the industry, get everybody over to 2.0. But for us, that is the next step. Now we want to harvest the big potential of ETP on the current adopted version of WITSML.
Yeah, this is Robert from Halliburton. Just one thing I want to interject also on that is that it's just not that much of a major step on your channel data to go from your 141 streaming data to your 2.0 streaming data. So once people see that, then I see that more people will go ahead and pick up 2.0.
And we're aware, but are not able to announce unless the people on the phone want to. Well, we are aware that pretty much every company is working on upgrading to WITS-ML2, even the companies that are already commercial on WITS-ML 1.4 with ETP. But if anybody wants to say when they think they're going to do that, that's fine.
Okay. So the next question, hi, this is Trushal. Can ETP be implemented using digital and cloud technologies or vice versa?
Well, ETP is a digital technology by definition. As far as the cloud goes, we have had conversations with all of the major cloud providers, all of whom are interested in creating a portal so that people could stream from a well site directly to the cloud rather than streaming to an on-premise computer center like the architecture Thomas was showing. You know, Thomas was showing that the data from Troll A went to Statoil, and from Statoil it went to Archer Oil Tools. Well, if there was already an infrastructure in the cloud to be able to stream from Troll A directly to the cloud, then all of the service companies associated with Statoil's drilling operations could pick up that real-time data straight from the cloud. There's nothing in ETP that either prevents or specifically encourages the cloud. It's just a matter of getting that infrastructure adopted into the public portals that are being created by the big cloud companies.
You know, and to that end, it should be noted that we are actively talking with some of the cloud providers to see how we can work together. So hopefully we'll see some movement there at some point. Okay, another question that came in is, in terms of data frequency rates and number of channels, how much improvement did you see using the new ETP protocol compared with the traditional WITS-ML transfer method?
Again, to give exact numbers, I would have to ask Baker and Kongsberg for help. But from our side as users, you know, at least for the pilot and for the subsequent tests we have done, it so far has satisfied all our use cases. You know, we have some use cases where they need higher frequency data sets onshore with sub-second latency. And so far, during our testing at least, we have been able to satisfy those requests. But with regards to any numbers or any more details, I'm not sure whether Baker Hughes or Kongsberg would like to comment.
Yeah, Ted, I think you've got some numbers actually documented from our tests, but from our side, from what we could see from Baker's side, and as Thomas has already mentioned, the latency was effectively only the network latency on all our tests. We didn't see any real latency on the data transfer.
Yeah, and Fred here from Kongsberg. I think during the test, which was from the rig to a central server onshore and then to another central server onshore, kind of two hops, we measured approximately 200 milliseconds per hop as an average, but that varied from 100 to 300 milliseconds. So it's absolutely sub-second rates there. And on bandwidth, I think we had approximately 1/10 of the WITS-ML based bandwidth when doing ETP. So it was kind of a tenfold improvement in response and latency, and tenfold also on bandwidth.
Okay, thanks guys. Another question is, are you able to provide more details about the firewall issues you had to work around and any other network configurations or issues you came across?
Yeah, again, Kongsberg or Baker, would you like to elaborate, or should we get back to that at a later stage?
From our perspective, Thomas, I think we'll get back to that one.
From Kongsberg's perspective, it was related to proxy settings, and we didn't include that in the first version and had to add a static proxy when connecting on WebSocket.
So there's a question for Thomas regarding connection loss. Upon reconnection, do you try to catch up with missed data? Is it buffered for a time period, or are there now gaps in the data stream?
Our strategy on that right now is that we use, with SAML 1411 with ETP for the real-time version of the data. And then currently, at least as an intermediate solution, we will use the old SOAP transport protocol to catch up with changes to data set, filling in gaps, so improvements made to the near real-time data sets. That's at least our strategy for now. And but I know that it's possible. The protocols are available, so you could use ETP for also making changes and handling the edits of the data. I'm not sure if anybody would like to spend half a minute talking about that, either Jay or somebody.
I will. That's Jay. So it's important to notice that, well, I didn't have time, obviously, to go through all the details of each of the messages in ETP, but ETP does support the idea that there are two kinds of sensors or computers that you may connect to. One of them might not have the capability to catch you up. You may have a really simple sensor that simply doesn't have a cache, it doesn't remember all of its old data. And in a case like that, you simply lose the data when the connection is broken. But there are messages for when you connect to a device that is capable of keeping all of the data cached in the event that a connection is broken. Then when you reconnect, you have the option of having it catch you up on all the data you missed. Maybe you just want to catch up on the last 10 seconds of data that you missed and have it, or maybe you don't care and you just want to catch up with the live. So when you get into the details of the protocol, you'll see that there's quite a few options for how to handle it. But we did have to account for the fact that some sensors, if you will, some of the remote devices may not have that capability. So we have this sort of two kinds of a normal streamer and a simple streamer.
Okay. And with that, we're really at the end of our time. I'd like to thank our audience for your participation, your questions, and I hope you like what you heard and that we'll hear from you in the future. And I'd like to thank Jay and Robert, who are here with me in Houston, Ted, Trond, and Thomas, who are coming to us from Norway, and Pete and Peter, who joined us from Aberdeen. Thank you, everybody, and have a good day.